All right, well, here we go. One last video for this semester. Today, what I want to talk to you about is how the universe is behaving based on our observations from here on Earth. So to do that, we've got to back up a few steps and understand a couple of things. One of these is something that you may or may not have learned already in physical science, but it is called the Doppler effect. So let me go ahead and write that down. It's fairly significant. Now the Doppler effect is something that happens when you have energy being given off in waves. So I have this picture right up here. You see my energy is traveling in waves, and you need to know that the top of a wave is a crest, the bottom is a trough, and the distance from one crest to another is called a wavelength, which I'm going to abbreviate with that symbol. It's a Greek letter called lambda, just to keep from having to write wavelength. In physics, that's the variable that we use for wavelength. So anyway, wavelength is just the distance between crests. Now sometimes when we draw waves, we don't draw them this way, we draw them this way. So I want you to imagine this is a fire truck. I know it's a terrible picture, but bear with me. Here's my fire truck, and this fire truck is stationary, and it's giving off sound from the siren right up here. Now we're going to pretend the sound wave goes out equally in all directions, and you can see these lines that I drew represent crests of a wave. So from here to here is one wavelength, one wavelength, one wavelength. And what you should see if I drew this perfectly is, since my truck is stationary, this wavelength should equal that wavelength. What that means for us in terms of sound waves is, for this person, it's going to sound the exact same as it would for this person. Now the Doppler effect comes in when the object giving off the energy, in this case my fire truck, is moving. So let's see what happens when my fire truck is in motion. So this fire truck is zooming towards this person. Let's assume they're on the sidewalk instead of in the road. That would be bad. So my fire truck is zooming towards this person, and you can see when it's moving, it releases a sound wave, but it catches up to the front, like this first crest. So what happens is, in front of my fire truck, you get a very short wavelength. What happens behind my fire truck, though? You get a much longer wavelength. And this is just a simple illustration of the Doppler effect. When the object giving off the energy is moving, if it's moving towards you, you will see a shorter wavelength. When it's moving away from you, you'll see a longer wavelength. And this is true of any energy that travels in waves. So it works for sound waves. That means this guy is going to hear a high-pitched noise. This guy's going to hear a much lower-pitched noise. But you know what else it works for? Dun-dun-dun. Stars. So here I have a star. Now this star, let's pretend, I'm going to zoom in a little bit real quick here. Let's pretend it's stationary. Okay, ignore my arrows. If it's stationary, it's giving off mostly hydrogen lines. So remember from a couple of videos before, we can use a spectroscope to see what a star is made of. And this star is made mostly of hydrogen. So these lines, red, teal, I guess I'd call it teal, I don't know, blue and purple, that's the spectrum for hydrogen. That's how we know that the star is made mostly of hydrogen. Now, since the star is sitting still, those are the wavelengths of energy it gives off. Now remember, let me jump back in right down here. What if my object giving off energy was moving towards us or away from us? It's going to create longer and shorter wavelengths. So let's see what that looks like for a star. I'm going to zoom back out. There we go, I think. All right. Okay, so let's do this one first. Since my star is moving, you know what? Let's see, I think I did my arrows wrong here. This is what happens when I try and plan this ahead. Let's just look at this side over here. Okay, let's just zoom in. Right over here. So, my star is moving towards the Earth. So if it's coming towards me, if I remember from my last picture, it should have a, whoops, get this pen to work, shorter wavelength. Now in terms of light, a shorter wavelength is this blue-purple end. So what you'll notice is I had 1, 2, 3, 4 lines, right? they are going to move towards this end. My red now looks orange. My teal now looks blue. My blue now looks purple, and my purple is right over here. Whoops. Problem is, this is the color I can see with my eyes. This is ultraviolet. So what happened is, since the star is moving towards us, its whole spectrum gets shifted. Now, the reason this is important is because when I look at a star, its spectrum is very rarely like this. It's usually shifted one way or the other. Now, if it's shifted a little, I know it's moving towards us slowly. What if it's shifted a lot? Now I know it's moving towards us really fast. What if it's shifted the other way, though? What if it's shifted to where it looks like, see, I did this wrong, get rid of this arrow. What if it's shifted like this, where the red becomes darker, and the teal becomes green, and the blue becomes teal, and the purple becomes blue? It's all shifted that way a little bit, towards the longer end. That tells me my star must be moving, yeah, ignore this one, away from us. So, if it's moving away, it'll appear to have a longer wavelength. If it's moving towards, it'll appear to have a shorter wavelength. And again, the real point here is, when the spectrum is shifted, it tells us the star is moving compared to us. How much it's moved tells us how fast it's moving. So that is how the Doppler effect works on stars. But, one more question. Does that work for galaxies? Like my nice picture of a spiral galaxy here. What if a galaxy was moving towards us or away from us? Could we use the Doppler effect to figure that out? Well, I'll tell you what. You know what the spectrum for a galaxy mostly looks like? Exactly like that, because galaxies are mostly made of hydrogen. So, if I could use a spectroscope on a galaxy, which I can, if its spectrum is shifted towards the blue end, it's called a, let me get my blue pen for effect here, hang on. This is called a blue shift, and that tells me it's moving towards me. What happens if it's shifted towards the red end? Guess what? It's called a red shift, and I know it's moving away from me. Okay, I have a stupid little scenario for how to remember this. I want you to imagine there's a rocket ship. There we go, close enough. Here we go, from the US of A. All right. Now, this rocket ship does not work unless you can see out. So I'm going to give it a windshield. The windshield is blue. So I want you to imagine this is you over here in space. If something in space is coming towards you, what color do you see? Blue. Just remember, blue shift is when something in space is coming towards you. What happens though if you're way down here and it's moving away from you? What color are you gonna see? The flames coming out my engines. So just a silly little way to remember this. If an object in space is coming towards you, it will have a blue shift. If it's going away from you, it will have a red shift. So let's look at the galaxies and see what we find. You know what we find? If you ignore Andromeda and the dwarf galaxies in our local group, if I go outside our galactic cluster, I find that every galaxy and every galactic cluster and every galactic supercluster is moving away from us. In other words, all those galaxies are getting further and further away. They're all redshifted. So this is going to lead us to a couple of kind of bizarre conclusions, okay? So let me show you what Hubble figured out about 100 years ago. He and some other scientists put their research together to realize something. They plotted their data, and this is what they saw, and it's called Hubble's law. As galaxies get further and further away, what do you notice about my data points? Their velocity gets higher and higher. So Hubble's law simply says this: if a galaxy is farther away, it must be moving faster. Now, if that's true for every galaxy, let me try and paint you a picture of this. This is easier in a classroom when I can like use you guys as props, but I'm gonna try with these dots. I want you to imagine each of these dots is a galaxy. Let me try to zoom it in again here. Imagine each one of these is a galaxy. Okay, let's just say this is us. There's the Milky Way. If all of these galaxies are moving away from us, they should be, I'm gonna put some arrows here so you get an idea. Okay, so these galaxies are moving in this direction, right? Okay, here's the weird thing. What our data tells us, what Hubble's law tells us, is if galaxies further away are moving faster, there's only one way for that to happen. So I want you to imagine we are not in the Milky Way anymore. I want you to come over here in this galaxy. Now, when you're in this galaxy and you're looking at Milky Way, it looks like the Milky Way is moving this way. Let's galaxy hop again. Now we're in this galaxy. Look at the Milky Way. If it's moving away from us, it looks like it's going that way. What if I were in this galaxy up here, looking back at the Milky Way? If all the galaxies are moving away from each other, which they appear to be, it looks like the Milky Way galaxy is moving that way. So which is it? Is it moving this way or this way or this way? Better yet, let's jump over to this galaxy. If I looked at the Milky Way, not only would it look like the Milky Way is going this way, but it's going to look like it's moving really fast. So which one's reality? Which way are we moving? I mean, this galaxy, which way is it moving? Because if I'm over here, it looks like he's going this way. It looks like he's going that way. Which way are these galaxies moving? And here's the cool part. They're not, but they are. They all appear to be moving without actually flying through space. The only way this works, the only explanation we can come up with to make this scenario work based on what we see is if this stuff right here and this stuff here and this stuff here is expanding. Now, what is that stuff that I just circled? That's space. Now, we used to think space was just empty space. That's why we called it that. But now we're starting to realize whatever this stuff is, it's getting bigger. Since it's getting bigger, it makes it look like this galaxy is moving away from us simply because this just got bigger and it got bigger. So we moved over a little bit, they moved over a little bit without actually flying through space. Space itself just got bigger. Now, common sense tells us if space is made of nothing and it's empty, something that doesn't exist can't possibly grow and expand. So, space has to be made of something. But at this point, it's something that we don't know how to measure, and we don't know how to detect, and we don't really know how to describe. We're just pretty sure space has to be made of something. Again, that's where like dark matter and dark energy come in. They're things that we're pretty sure exist. We just don't know how to describe them because we don't know exactly what they are. So I guess the reason I wanted to take you down this path was because I wanted to talk to you about the Big Bang Theory because it's something you're going to hear, and I just want you to have a clue what it means. Okay? There's lots of ideas and stuff out there, but at its simplest, the Big Bang Theory is really the opposite of what I just tried to explain to you. So let's work backwards. If space is expanding right now, go back in time. What happened to space? Well, space must have gotten smaller. It contracted, right? It's the opposite of expanding. So if I go back in time even further, then space contracts even more. What happens to my galaxies? They get closer and closer and closer. What happens if I go back in time an almost infinite distance? The galaxies get closer and closer and closer until every galaxy has to be really, really close. Now I want you to go back in time even further. What happens to those galaxies? Okay, so that takes us to the Big Bang Theory. Okay, I'll get to that in a second. The Big Bang Theory, at its simplest, just says this. A long time ago, all the matter and energy, everything that exists in the universe, used to exist in something very small. We'll say the tip of my pen here. Bing. Everything that exists, everything, was in a small area. For whatever reason, it started to expand. So not really an explosion, so I don't know if Big Bang's the right word for it, but it's a big expansion. So it starts to expand violently, and it continues to expand, and it's still expanding today. So why did we come up with this idea? Because it really doesn't make a whole lot of sense, right? If you go back to this idea that the galaxies are all moving away from each other, which we can see, and you work backwards, everything has to get closer together. So the Big Bang is really just an explanation of why this is happening without a whole lot of details. Now, there's lots of other theories that go along with it, but that's in a nutshell what the Big Bang Theory says. And I see my video is getting a little long. I'm really sorry. I'm almost done. I have one more thought that I really think is worth pondering, and so I'm going to toss it out there for you. Let's pretend the Big Bang Theory happened, which nobody was around to see it, so it's kind of hard to, justify that it did or didn't. But let's pretend it did. Let's pretend all the matter and energy in the universe was in a small spot, and now think this through with me. What does a telescope do? A telescope lets me see deep into space, right? Now realize, when we look deep into space, we're looking back in time, correct? So if I'm looking deeper into space, I'm looking deeper back into time. If I look at something that's 1,000 light years away, I get to see 1,000 years back in time. If I'm looking at something 100,000 light years away, I'm looking 100,000 years back in time. So hypothetically, if I could build you a telescope that could look an infinite distance into space, let's just pretend I could, and I sent you all home with one tonight, and I said, hey, I want you to take this outside tonight, and I want you to see the Big Bang as it's happening. You should hypothetically be able to do that, right? Because you can see an infinite distance into space. My question is, when you set up your telescope, which way would you look? Maybe I'll have one of you look west, one of you look east, one of you look north, one of you look straight up. And you know what the crazy part is? If all the matter and energy in the universe, if everything that exists was in a small spot right here, this is everything. When you look off into space, it doesn't matter which direction you look, because the Big Bang happened everywhere at the same time, and everywhere is right here. So if you were to look into space in any direction at all, far enough, you'd all see the exact same thing. Now try and picture that. You're all looking different directions. But if you look far enough into space, you see the exact same thing? Question mark? Anyway, worth pondering for half a second. This leads us to all sorts of questions and problems and puzzles and things to think about. And if we were in class, I would take your questions and I would try and answer some of them. But as it is, this is where I'm going to leave you. I drug this on long enough. Thanks for bearing with me. This will be our last video lecture for this semester. Thanks for all your hard work, guys. You've done a great job.